I'm Niels Köster. I work at the Virtual Vehicle Research Center in Graz. We are like a research center with around 300 people. We do lots of different things with lots of different groups. I personally work in the battery group. And in ARCHIMEDES, I work on supply chain 3 on Demonstrator 2. There are other people at Virtual Vehicle who work on Demonstrator 1, which is a rescue dog, but I only work on the glider, the BMS system there. So the work in ARCHIMEDES, which Virtual Vehicle does on Demonstrator 2 is in 3 parts. It's a functional safety. The second part is the thermal runaway experiments, where we blow up the cells in essence and see what happens. It's mainly safety. And the third part is centered around aging, the battery aging, which is split in 2 parts again, the experiment and the aging modeling and simulation, which then is used from SAL for their BMS machine learning and AI models. They provide the data, we provide the simulated data, and they then build the machine learning models, which then predict something, hopefully. So let's start with the aging, because we have different key factors, let's say. For the aging, in ARCHIMEDES we work with ICE. ICE sensors, and ICE sensors often makes frequency-dependent models. We have sinus curves and we get an impedance, which is a frequency-based model. Very standard in battery modeling are time-based models, RC models. And in ARCHIMEDES we try to connect like the time-based RC models to the ICE simulated, so the frequency ICE model, so that we actually get the same frequency response from the time-based models from only time-based measurements. So no frequency measurements. We do frequency measurements, but they are validational measurements for the modeling. And that is a very big part because both are very connected and used for different things. And if we can connect them together, the frequency and the time-based model, that is, and we have done first steps there in the comparison. For the thermal runaway part, I think the big part here is actually to define a safety rating. So let's go back. In thermal runaway, which is the exothermal reaction of the battery, where the battery heats up in like, let's say 10-20 seconds from 150, 175 degrees to 1000 degrees. And a lot of gas comes out of the cell, and sometimes even the cell comes out of the cell. It flies out, especially in this kind of cells here. But in the experiments, you often only see thermal runaway happened or didn't happen. So that is the main, especially in propagation, and we have done work on that project to get kind of a safety rating. How far away are we from? So kind of like bridges, when you have a safety rating of 2, you need 2 times the force which we applied to then go to a safety case where something happens. Similar here for thermal runaways, we go over an energy-based method where we measure the energy going in. We do cell experiments beforehand where we apply different energies. We then look at how broken the cell is afterwards. It's not always thermal runaway. Sometimes it's the current interrupt device goes well, or sometimes it's just the voltage is broken, but the current device is still working and stuff like that. And then we want the next step. We do the experiments on the actual model, where we can then look at how far away or how close. We don't expect the thermal run to happen. This product is very safe. They designed it that way. So we want to see how far away we actually are. Do we need like maybe 20% more energy, 50% more energy, or 100% more energy than the thermal runaway? So one cell goes in the runaway, it applies energy to all its surrounding cell and maybe into the gas to cells in the different model. And we can for each cell see how far away we are from the thermal runaway. And that is something I don't think has been done before. We have not seen it, and like it's standard for like other things like bridges and stuff like that. We do this kind of safety rating is very standard there, but it's not happening for thermal runaway yet. And I think that is the big achievement from our side, from the thermal runaway side. I can certainly not speak about the functional safety. That is not, I don't know enough about this. Lifetime for batteries often is very deeply connected to aging. So, because that is, in a sense, the lifetime of a battery. For normal like operations, aging means, for example, degradation of capacity. And you normally speak of an end of life in a car, and also here when we have reached 80% of the initial capacity. So aging experiments and how the cell ages and how you maybe can do different things, which is then going to be done by ZAL. They test different kind of charging or flying or whatever, or storage to limit aging as much as possible and detect aging also, and maybe change modules before they are so broken that they affect other cells and other modules and other components in the whole train. So that is from the aging part. Similarly for the thermal runaway part, so thermal runaways do happen, and sometimes you don't even notice them, especially with the small cells. They go up and then the cell is gone and you suddenly not have 22 cells in parallel, you have just 21. Hopefully, in the best case, can be different things, often crash, but I mean internal short circuit, overheating, overcharging, stuff like this are the normal things, so they do happen. So, but detecting that something really happened or is about to happen is a very important part for ensuring the safety of the pilot, but also of the rest of the components, which then extends their lifetime. Not the cell is gone, yes. But hopefully the other components are not. Thermal runaway propagation, that means the chain reaction. That is what we want to prohibit. That we often have a problem that maybe one cell goes because it's broken. It was already broken when it was delivered and we can't detect it. But we don't want that the one cell which is broken affects the other cells, which is the propagation part. For me, it's a safety rating, personally. The thermal runaway safety rating, it's a very simple but neat idea from my colleague Andrei Golokov, who is the leader of the thermal runaway experiments. And I want to see how that works and that we can actually detect in the module how far away we are. Because that is, module experiments are a bit complicated because putting sensors in the modules without destroying them or changing them enough that the experiment is unvalid is very difficult. So you can see it here. Getting a temperature sensor somewhere in here without destroying it is not really easy. So often that's why the module experiments are limited in data to only thermal runaway happened. And that is without changing the model. In this case, we actually worked with Advantech. They built the sensors, you can see them here, and the heating plate directly into the module. So we don't have to take apart the model. In the construction process, we have all things in here already, which is very good. I'm also excited about this, that normally you have to take them apart and then the modules don't really work as they're intended originally from the person. But here we actually have the person who built the module, or the packaging in this case, put in the actual sensors and heating equipment, as we are as close to a real model as we can actually get. And that is a bit special because normally we have to take it apart, put heating inside, and then put it back together, and it never quite is the same as it was when it was delivered.